Hello everyone, thanks for joining in. I'm super excited to be here at presenting at PyData Global. Feel free to ask me any questions. I want the session to be interactive. I have kept the slides minimal. I'll be going through documentation, how to get started with training, and how to check out evaluate different kind of accelerators. Let's go. So this session, I'm going to talk about TPUs, GPUs, multiple accelerators, distributed strategies, etc. Before starting with the session, little bit of introduction about myself. I have spent like good amount of time working on open source. So I used to work as a senior research engineer at Lightning AI. It's a leading MLOps company, and I was also an open source maintainer of a framework called PyTorch Lightning. So this is the agenda of our session. We'll give like an overview of ML accelerators like TPUs, IPUs, Habana. Then we will discuss the fundamentals of distributed training. And then we will discuss about the TPU accelerator, how to like do distributed training on that and get started with it. And at the end, we'll have like a quick summary of what we discussed and how you can get started with it. And we'll also have like a 5-minute AMA to like answer your questions. Awesome. Overview of ML accelerators. So right now there's a huge innovation happening in this space. You will see like a lot of funding news. A lot of companies are getting funded. A lot of companies are building accelerators, like which is like optimized for like processing machine learning workloads. But before getting into the ML accelerators part, I want to discuss a bit about the machine learning lifecycle. So machine learning lifecycle depends heavily on data and the model, right? So the quality of your model depends very heavily on the quality of data. So it's very important to build a paradigm around that. So that's why accelerators, the different kind of accelerators, like for example, some accelerators do well with inference, certain accelerators do well with training, and certain accelerators optimize on like different kind of machine learning problems like NLP or computer vision, etc. So this is all the different kind of accelerators I've worked on. The first one is a very common one. The first one is called CPU, Central Processing Unit. Everyone has worked on it. And second one, which is like a game changer for the deep learning world, it's called GPUs, Graphic Processing Unit. So it's a very common one, was the most popular one because it's supported by NVIDIA and it is based out on CUDA. So you will see a lot of people training their huge models on GPUs, and it's very easily accessible right well. It's available on AWS, Colab, etc. And the third one is called Habana. Habana is something that was developed by Intel. So one good thing about Habana is like it's very cheap, it's very reasonable, and you can get started with it as soon as possible. You can get access to Habana on AWS machines, and you can check out their tutorials on PyTorch Lightning docs and even their own docs as well. And the fourth one is TPU, which will be the focus of this session. TPU is Tensor Processing Unit. It's the hype because it is supported by like multiple AI frameworks like TensorFlow, PyTorch, JAX, and you will see a lot of academic papers being published around that. And it also has like a lot of companies are also using it in their production systems as well. And the fifth one is IPUs. So IPUs was built by a company called Graphco. It's based out of UK, and it was at one point was like one of the most funded ML companies out there. And the last one, but not the least, the MPS. MPS is developed on Silicon M1 chips, which is available on your Mac machines. Like a lot of people have their Mac machines, they can start training on that, and it's like there's a lot of development going on towards the PyTorch side, and it's been like a good amount of development. You can check that out as well. So this is like an overview of how there are like a lot of new upcoming accelerators as well, like cerebral systems, which supports the training of huge models on like a single chip. And so these accelerators have like different kind of pros and cons. And for example, one way to evaluate accelerators is like checking out the MLPerf benchmarks. How do they perform against multiple models, like different kind of models, like NLP models, transformers, computer vision models, generative, like stable diffusion models, etc. And the second way of to evaluate accelerators is like how's their support with the framework, right? How does it do well with PyTorch, TensorFlow, JAX? Like JAX does really well with TPUs, so you can check that out as well. So this is like an overview of about different kind of machine learning accelerators. Next, we are going to cover distributed training. So distributed training. So you must know like there's been a huge like a lot of research and development in this space in the last few years. Like you see like a lot of models, like huge models with like billions of parameters being trained and a lot of academic research being published. Almost every week you will see like new kind of research out there on Twitter, social media, etc. So why are people getting into distributed training, and like why is it necessary at this point? Right? So at this point, I can think of like main three pointers, right? If you want to like increase the efficiency of your training, you might start with CPU, but it's like a bottleneck. You can't train it on multiple machines. So you check out GPUs. So if you want to like make your training process faster, you need distributed training. You need multiple machines to train your models. Second, if you want to like fit in like large data sizes of data in one machine, you need huge machines, right? For example, you have this data load, a data set of like thousands of samples, data samples, but you want to like distribute it across multiple machines, you need distributed training. And the third one is if you have a huge model, like if you have a model with billions of parameters, you can't fit it on one machine. That's when you need that's when you need like a parallelization technique which will split the model into multiple machines, and you can do the forward pass or like this like training the model. So these are like various reasons why you need distributed training. But for example, when I got started with distributed training, it was a bit challenging because there was like a lot of boilerplate. You have to so like a lot of like moving parts you need to take care of. Need to create wrappers, which is like also repetitive code. So there are like multiple ways you can go wrong with distributed training. So I will discuss in brief how you can like not fall into that trap and get started with it. And also I will also discuss in depth about different like the core distributed training strategies. All right, the two main paradigms of distributed training I'm going to discuss is data parallelism and model parallelism. So what is data parallelism, right? So I will show this small diagram of different kind of parallelism techniques. The main one is the main paradigm you should think of is like it might sound like overwhelming and like a bit confusing, but stay with me. So data parallelism is a strategy where the data is split into n parts. Imagine you have four GPUs. You have access to four GPUs, which is great. But how do you split that? How do you train models on that? So one way you can look at it is like you have this amount of data, like 1,000, 1 million data samples. So we can split the data into n number of parts. And just think of this like your model. You have this ResNet model. Then ResNet, it will be the same model on every GPU. The data is split, and each GPU will see that part of data for every epoch, for every training process. So that's how training data parallelism works. So there are multiple, like there are like n number of GPUs. The data is split into n number of parts. Is the same model on every GPU, and the weights get updated every time. And it's the same model at the end of the training process as well. Got it. Just imagine there are five GPUs. The data has been for there's a forward pass that happens. Then the gradients get calculated, and the gradients are collected and they're averaged across multiple GPUs. And the same gradients are sent to the backward pass. Hence, the weights are same across the training process. And the second main one is called model parallelism. So model parallelism happens when you split the model, when it's like not possible to fit the entire model of one machine. So it's like one bunch of data that's been passed to the entire all the machines, like, and this is how it's processed. Just imagine like a sequence of like multiple parts of model. That's how it works. So data parallelism, model parallelism, and they're much more like optimized distributed training strategies, which are going to cover next. All right, so before going to the multiple different strategies, like optimized strategies for like distributed training, I'm going to share this architecture overview we used to follow at PyTorch Lightning. As you can see at the left side of the diagram, there are loops, which is like the training loop, validation loop, text loop, prediction loop. This is just an overview of like a for loop for the deep learning workloads. As you can see, the strategy box, like a paradigm handles the accelerator. And we also have a precision, cluster environment, and checkpoint IO. The accelerator refers to the hardware being used for the training or the inference purposes. And we have this base class which handles it, and the second is the precision, and what precision you want to like train your model or run the inference for. This helps to like reduce the memory or like faster training or inference processes. And cluster environment, which is the third one. So cluster environment takes care of your cluster setup, like how's your GPU setup, etc. And fourth one is the checkpoint IO. Checkpoint IO plugin. It's called a plugin which handles the saving and loading of checkpoints, also across multiple machines, how to handle that, and the fourth, and also like how to delete checkpoints, etc. So when you think of accelerators, don't just think of it as like just hardware. It's an entire ecosystem. It comes with like that ML compilers. Also think if it's like accessible through your cloud services. Is it available on GCP? Is it available on AWS? It depends on that as well. So like a lot of people also use slums at like academic research labs. So we also have support for that. All right. Next, PyTorch Lightning. So I'm going to cover a bit about PyTorch Lightning. How does it work and how it can help you with your deep learning projects. So PyTorch Lightning, it's a lightweight PyTorch framework which helps you with scalability and efficiency. It is like supercharged with multiple features. I will go to a documentation to give a hint of how it works. So this is the PyTorch Lightning repo, and we can get started from here. We have a good README, and this is a design philosophy we can check. We try to help you with flexibility. For example, if you have like existing PyTorch code, how to move to PyTorch Lightning. But before that, I want to like introduce you to like two main paradigms of PyTorch Lightning. The first one is called a Lightning module, and the second one is called a trainer. So Lightning module is where you like define your research code. This is where you like define your layers, how to do the forward pass, how to do the training step, etc. So I'm to go through like a small minimal version of a Lightning module. So you subclass the Lightning module and you define the layers in the constructor. And there's this forward a method you have to define, so how the forward pass should happen. And there's this training step. For every training step, how should we like process the batch, and what kind of loss you can return. So that would be the loss. And this is something called a self log. So we also support like multiple kinds of loggers, like TensorBoard loggers with some biases. So you can just define the logger, and you can just define the metric you want to log as well. Like you're defining like training loss, right? Here, MSC loss is also the loss function, so you can like return the loss function. And we have one more method called configure optimizers, which like support multiple optimizers, and like where you can like return the optimizer you want to use. So we have one more method called configure schedulers, which is helpful, like which you can also integrate with your Lightning model. So in brief, Lightning model is where you define your research code, your PyTorch code. So if you already have like a code base of existing PyTorch code, this is where you move the research code. Got it? And the second one is PyTorch Lightning Trainer. You must know, like sometimes when you work on deep learning projects, there's a lot of boilerplate involved. So our main philosophy with PyTorch Lightning is like we want to reduce the boilerplate. We want people to focus on research, do not get into the hassle of like handling the engineering part. So this is what the trainer does. It is supercharged with like multiple features like precision, callbacks, how to handle the checkpointing, etc. So this is how the trainer works. The training part works. First, to like define a data set like a data loader. Then we define the Lightning model, which is the models. And third, we define the trainer, and then we call the dot fit method on like the model, the data loader, etc. So in brief, again, I will cover this again. So this, we have a Lightning model which defines your research code, where you can move your existing PyTorch code or like write the pure research code, like define the layers and the models. And second is the trainer, where you can like, they're like, we support like multiple flags, which I'm going to like cover now. All right, let's go. So I'm just going to show you different kind of trainer flags. So what are the different kind of trainer flags we support? As I mentioned in PyTorch Lightning, we support like multiple kinds of accelerators. So this is so the three main flags to handle distributed training or like training on different accelerators is accelerator devices and strategy. So just pass the accelerator flag to trainer. It could be either be CPU, GPU, TPU, auto. So we also have this flag called auto, which auto recognizes the accelerator on your system. So the same script can run on multiple machines. And the second flag is devices. For example, you have like five GPUs. So you can define devices equal to five and accelerator equals to GPU, right? And it will figure out the number of GPUs available on your machine and start training on that. See, as you can see, like you don't have to handle the distributed training logic. You don't. It's very hard. It's very easy to like get into the rabbit hole and get distracted from the research and like mess up your training process, right? It's the same with TPU. Just define the accelerator as TPU and like define like one TPU machine as eight TPU cores, and you can get started training with that. And the third important strategy flag is called strategy. So we support different kind of distributed training strategies. So it's DDP, DDP spawn, deep speed, colossal AI, etc. So we can just pass the flag to the trainer object, and it will handle the engine logic for you. So these three are like one of the top like used flags for the trainer class. We do support multiple more flags like accumulating gradient batches. Like for example, when you are doing the training, it accumulates like you want the backward pass happening, the gradient accumulation happening every n number of batches. Like accumulate gradient batches equal to six. It will happen after every six batch returns, right? We support auto scale, we support auto select GPUs, which will, if you don't know the number of GPUs present on your machine, it will auto select the GPUs available on your machine and figure that thing out. We also have a flag which will help you auto detect the right learning rate for your training process. We also have this benchmark which will help you like find the bottlenecks in your research code. And we have something called callbacks where we have defined multiple life cycle methods, hooks for your training process. For example, you want to implement something before the training step works, after the training step works, after a batch of the training step is executed. So we have like multiple hooks where you can implement and like pass it to the trainer object. For example, we have this print callback, which you want to say like on train start, and you want to print that during the training process, on train end when the training is done, right? You have to just you have to first define the callback and then pass it to the callbacks flag to train, right? And in machine learning, it's very important to check the performance you're training on validation as well. So if you want to like check how is it working, we have this flag called check while every n epochs where the training is working, but after every 10 epochs, training epochs, you want to check, how is it working? How's your model working on the validation data sets? So we also have that as well. We have discussed devices, we have discussed, so we also have this flag called enable checkpointing. There must be times you don't want to save the checkpoints, you just want to check if it's working or not. So we can just, it's a Boolean flag where you can define true or false. One second. So these support more than 40 features. We can check them out. It's very easy to use. We handle a lot of engineering knowledge for you, etc. We also support different kind of progress bar. We support TQDM, breach progress bar, and we also support a flag called number of nodes. For example, we have cluster of 256 GPUs, which is available on different kind of nodes, right? So you can pass a number of nodes is equal to 8. So we can handle cluster logic for you too, right? So this is trainer. We discussed trainer, and here is the lightning model. So as if you have written PyTorch code before, you would know like you have to define like a for loop to, and like you have to like pass it to the devices like dot CUDA dot to this device. You don't have to do it with lightning model. You don't have to define dot CUDA dot to this device. We handle that logic for you. So you have to just write like hardware agnostic code with lightning model, right? As we discussed, you have to just define the forward method, the training step, and you have to also define like a configure optimizers to what optimizer to return. Right? In the documentation itself, you can see different kind of methods we support. So this is like a basic for loop when you just use like vanilla PyTorch loop. First you have we call like dot train to put the model in the train mode, so it can enable like gradient calculation. Then we have this for loop where we are iterating towards multiple data samples of a data loader. Then we first call the training step, then we add it, then we calculate the loss, then we like clear the gradients, then we do like a loss backward to like find the optimize to update the parameters as well. So you don't have to write this logic. We handle the logic in our strategy classes. Awesome. So we have covered a bit about PyTorch Lightning. We have discussed the main two paradigms, Lightning module, which handles the research code, and trainer, which handles the engineering code for you. Awesome. What's next? So the TPU architecture. So I'm just going to give an overview of what TPUs is. So TPUs is something, it's tensor processing unit. It's optimized and it was developed. It is optimized for like machine learning workloads, and it was developed by the Google team. It's available on GCP. It's available on our Kaggle, it's available on Colab. You can check them out. So the why TPUs is such a hype. A lot of research papers are using TPUs from Google, Meta, etc. So TPUs is to have like a very strong support from TensorFlow, but it's the development has been very impressive with PyTorch as well. So you can get started with like PyTorch on TPUs too. And like the Google has this research program where you can apply to and get access to TPUs. So this is just an architecture layout of TPUs, and like as you can see, it has something called like a matrix multiplication unit, which is like 128 plus 128. There are multiple kind of machines, which is the V4 is the recent TPU architecture, which was like launched very recently, and you can have access to that. As you can see, these are the TPU chips, and like for every 8-core TPU chip, there's like a TPU host. You can SSH to the TPU host and get access to that GPU chips. So this is how it works. Like you can go to your GCP machine and we can spawn up a machine, and you can like SSH to this via TPU host to your VS Code or like any other ID you like, and then you can start coding on that. So back to how to get started with like PyTorch Lightning TPUs, we have this page. So if you go to the PyTorch Lightning documentations, we have like different kind of levels. We have basic skills, intermediate skills, advanced skills, and expert skills. So based on your level of expertise, what you want to learn, what you want to experiment with, you can check out the skills. And then we have this documentation for every kind of accelerators like GPUs, HPUs, IPUs, TPUs, and also like the M1 chips, right? You can go to the TPUs chips. We have different kind of categories, like how to learn the basics of like training on single GPUs or like multiple GPUs, how to scale like massive models or using cloud TPUs. There's like advanced on like how to do debugging, and there is FAQ to troubleshoot for like troubleshooting your models, right? So, but before getting into this, I want to like cover why we need PyTorch Lightning for this, right? What if I just want to use the vanilla PyTorch code to write code for like to train models and TPUs? So there's a repo called PyTorch XLA, which handles the TPU logic for training PyTorch models. If you go through the documentation, it's very similar to how you train on GPUs. So these packages, Torch XLA is available when you like go through the when you SSH to the TPU machines. It comes with the predefined like, Torch XLA packages. So this is where you're like defining a tensor. You have to like define the device it's trained on, and you will get a tensor which is available, which is like present on the TPU devices. So you accelerate tensors are PyTorch tensors basically. This is where you can start working with tensors and models. So how to do like a simple training on like imagine this like a TPU chip. One TPU chip has like 8 cores. So when you train on like one single TPU core, you don't need to do distributed training. But if you're training on like 8 TPU cores, you need like some kind of strategy to train on it. This is a simple PyTorch loop training loop to like train your data. We are like clearing the gradients. We are sending the data to the TPU device. We are sending the model to the DPU device, and we are doing a backward loss. We're updating the optimizer parameters as well. So this xm.mark step is when like the all the processes stop and they check if the parameters are getting updated or not. So this is for like a single TPU device, but they also have support for like multiple TPU devices. So they use something called dot spawn. So this is how it works on like multiple like 8 cores. As you can see, the code changes a bit when you're training on like single TPU device or like multiple TPU devices. So there's something called pod TPU training as well, where you like train on a collection of multiple TPU chips. We do have support for that as well with PyTorch Lighting framework. We were like one of the first like frameworks to do that. Like let's have like active support for that. So you can check that out as well. So as you can see, there's a lot of boilerplate. It's the same code if you're like defining for multiple machine learning projects, but with PyTorch Lightning, you just have to mention I said it's good to TPU. We handle the hardware logic for you as well. So I would just want to check the time. Should I open the chat? Should I answer some questions here?
Yeah, I was actually looking through it. I don't see any question being posted at this moment. Um, yeah, but I think we still have about like 3 to 4 minutes left. You wanna
Awesome,
be
awesome.
yeah.
Okay. So I'm going to also like go to a doc how you can like start with training on like 1 trillion plus parameter models, and I'll go through that as well. So PyTorch has something called distributed data parallel, which handles the training logic for you. Like it handles where you are it's like a wrapper on your model which you have to define. We support different advanced distributed strategies like colossal AI, which is doing great. We also support fair scale, which is by Meta. We support sharded techniques, which like is optimized for like cutting down the memory, etc. So do check it out. Do reach out to us, like reach out to me on Twitter, social media, etc. If you have any questions regarding that. As you can see, if you want to like enable fair scale, you have to just pass FSDP, which is like fair scale implementation of data distributed strategy, and you can also define the precision you want to use. It's like 32, 16, less than that. Yeah, do check it out. So do get started with TPUs. It might sound overwhelming, but it's very easy to get started with TPUs, and like there's been like good amount of development happening. It's a bit stable, and there's always like a PyTorch accelerating which is like there to help you out.